Hello everyone, I'm Ning from the Institute of Computing Technology, Chinese Academy of Sciences. It's a great honor to present our latest research work today, MD-Pipe. MD-Pipe is a strongly scaling microarchitecture design for ab initio accuracy molecular dynamics simulations. I will introduce our work from the following 5 aspects. First is the introduction part. Molecular dynamics is a computational method to study the motion of microscopic molecular systems. MD technology has been widely applied in multiple fields, including the research on mental defects and analysis of biological reaction processes. In recent years, neural network-based molecular dynamics methods have gained widespread attention due to their significant advantages. Such methods utilize first principle accuracy data from training, and the obtained models can achieve accuracy comparable to first principle calculation during inference. Although the NMD method significantly reduces computational complexity, its simulation speed still fails to meet the requirements of practical applications. Take the mental defects reaction as an example. The actual process only requires microsecond level observation, but the existing technology needs up to a week for the simulation. The current strategy of increasing computing resources to improve speed has encountered bottlenecks on general-purpose processors and supercomputing platforms. Because the atom granularity reaches that each computing unit only processes a single atom, and the task is hard to be further divided. Therefore, we need dedicated hardware to enhance the simulation speed of NMD. Next is the background and motivation of our work. The DeepMD kit is currently the most widely used method for calculating NMD potential functions. In fact, its related work won the Golden Bell Prize in 2020. Now, let me work through how the algorithm works. First, it selects the neighbor atom pairs for later calculation. Then, it extracts atomic structure descriptors during the embedding process. After that, the fitting net calculates and outputs atomic energy information. Finally, in the backpropagation process, energy gradients are converted into atomic forces. One important thing to note is that this method still requires gradient computation during the inference phase. That is because atomic forces are obtained by differentiating the energy function, which is a key feature of this approach. As mentioned earlier, the performance gain from software-based approaches such as distributing atomic computations across more cores has reached their limit. To achieve further improvement in parallel processing, we must shift towards specialized hardware accelerator architectures. Task-level parallelism presents an intuitive path to enhance molecular dynamics performance, yet it remains insufficient explored. Simply applying basic pipeline to task fails to improve the computational speed of individual atomic simulation. The key solution is a fine-grained pipeline for task-level parallelism. The core lies in overlapping computational workload between tasks. Only through this method can we effectively enhance the performance of per-atom simulations. Based on these findings, we propose the MD-Pipe architecture design. The overall structure of MD-Pipe is made up of 4 core models, and I will work through them from right to the left. First is the FitNet. This is a 6-layer fully connected neural network. Next, the descriptor model primarily handles matrix transportation and reduce dimension through flattening. Moving on to the embedding, its main job is to perform polynomial calculations. One thing to note here is that during gradient computation, it needs to temporarily store intermediate data. Finally, the filter model comes into play by filtering data based on atomic pair distances. The design is straightforward, but to achieve a fine-grained pipeline, we still need to address the 3 key challenges. First, we have the systolic array bubble problem. Due to the injection and the drain time, the systolic array can stall, reducing efficiency. To solve this, we introduce the high utilization systolic line, which minimizes idle cycles and keeps conceptions flow smoothly. Next is the data flow blockage issue. In the descriptor, matrix transpose operations can create bottlenecks, disturbing the pipeline. Our solution is a preloading and data flow rearrangement strategy, which ensures continuous data movement and eliminates unnecessary delays. Finally, there is the storage resources overhead. Specifically, the embedding's backward computation demands high memory usage, which can be costly. To optimize this, we apply a computational migration, reducing memory overhead while maintaining performance. In FitNet, we employ a high utilization systolic line to completely emulate bubbles. The key innovation here is our single-line systolic array, which works hand in hand with a fixed output systolic strategy. To optimize performance on top of that, our adaptive computing unit is designed for maximum utilization. Each layer has its own customized cell structures, which is adjusted to balance computation demands between layers. As a result, we further eliminate the bubbles between layers, ensure a high efficient workflow. Next is the data flow rearrangement. Originally, we faced a bottleneck in the descriptor model, which consumed 128 computation cells. To address this, we introduced an optimized approach by replacing it with the structure in the right side. This simple change reduced the computation cell usage to 16. Additionally, we propose a transpose elimination technique. Since the subsequent models flatten the matrix D from 2-dimension matrix into a vector, we ensure the consistency in the results by adjusting the parameter order in FitNet. In this way, there is no need to transpose the matrix. Lastly is the calculation migration. Now let's talk about the original design flow. In the filter, we temporarily store the environment matrix R and DR, which requires 64 bytes per atom pair for storage. To address this, we develop an optimized approach. First, we structure the computational workflow to follow the order of center atoms. Then we migrate the calculation of R and DR to the embedding gradient phase. Because of these improvements, we successfully reduced the on-chip SRAM storage requirement to just 20 bytes per atom pair. The next is the evaluation of MD pipe. First is the atomic system and computation platform configuration we used. For the software setup, we employed the LAMPS in the December 2022 for MD simulations. Additionally, we utilize DeepMD Kit version 2.0.3 for deep learning potential model, which we further customize to fit our need. Moving on to the simulation systems. We test various systems, including copper, water, and other systems. Next is the hardware platform first. For the baseline on supercomputer, we use Fugaku with 48 computing nodes. Next, for the baseline GPU server, we deployed an NVIDIA A100 with 40 gigabytes of memory. For the FPGA implementation, we deployed MD pipe on an AMD VPK180 series FPGA running at 250 megahertz. Finally, for the ASIC design of MD pipe, we synthesize it by using design compiler at a 12 nanometer process node, targeting a clock frequency of 2 gigahertz. First, we made the accuracy evaluation. As mentioned earlier, we made some modifications to the computational workflow of DeepMD. Specifically, we focused on two key changes. First, we deployed the calculation from the R and DR matrix. Second, we convert the flatten process of matrix D into flatten the transpose of D instead. Now let's talk about the accuracy evaluation. We evaluated the computational errors in forces and energy across 4 different atomic systems over a single time step. The result shows that the neighbor of these two changes had any significant impact on the accuracy of MD pipe calculations. When it comes to the performance of physical system simulations, we have achieved a big acceleration. We first compare it with supercomputer platforms under extreme strong scaling conditions. MD pipe achieves 454 times speed up compared to the total work in Fugaku supercomputer. Now, look at the comparison with A100 GPU. The ASIC version of MD pipe is 23.7 times faster than a single A100 GPU. And even the FPGA version shows a significant improvement with a 2.97 times faster performance boost over A100. Finally, we evaluate the power and error test results. First, we achieve significant improvements in both performance per watt and performance per error. Compared to the A100, MD pipe acquires over 2 orders of magnitude better. And in FPGA environment, the advantage is particularly clear. Here the performance per watt is an order of magnitude higher than the A100. Now let's move on to the conclusion. MD pipe achieves significant improvements in simulation speed and resource efficiency through several key technologies. First, it employs fine-grained pipelining, which deeply optimizes the computational workflow and dramatically accelerates the simulation. Next, the high resources utilization design eliminates the bubble effect common in systolic risk, preventing computational bottlenecks and maximizing hardware efficiency. For data flow optimization, MD pipe introduced 2 strategies, data rearrangement and preloading. This effectively reduces the overhead of matrix transportation operations. Finally, the computation migration significantly cuts down on-chip memory cost. So this is the end of our presentation. Thanks for your attention.
Questions?